Whose life would be better if you knew more C++? Whose life would be better if your coworkers knew more C++? Let's get started.
Good morning. My name is Marshall Clow. This is the Down the Rabbit Hole and exploration of Stack Overflow questions. And we're going to be talking about problem solving and reading other people's questions and things like that. Okay, about me, because everything's always all about me. My name is Marshall Clow. My badge says my name is Inigo Montoya. It's a long-standing joke. But I have been programming professionally for a long time. Got my first job, it's going to be 40 years next year. Anyway, I've been involved at Boost continuously since about 2000. For a long time, until very recently, I was the co-donor, the lead engineer for libc++, the standard library implementation in Clang. And that's the standard library, by the way, that ships on every iOS device, every macOS device, every Android device. So if only I was getting royalties, I suspect I would be really, really well off, because that's 1.5 billion devices a year. But it's open source, so no, I'm not getting royalties. Anyway, I was also, for 5 years, I was a chairman of the library working group on the standards committee. 5 years is a standard term, and I was quite happy to turn this over to Jonathan Wakely and Jeff Garland and Dietmar, who are now doing the job very well. Anyway, let's dive right in. Okay, sometimes when someone asks you a question, it's a very simple, straightforward question. They want a simple, straightforward answer. Is 37 a prime number? That's easy. Yes, it is. Okay, but sometimes, especially in technical discussions, people have thought about a problem they're trying to solve, they've roughed out a solution in their minds, and they're working on implementing that solution, and then they get stuck. And frequently it's just, I just have this one little part I don't know how to do, and maybe you can help me with. And the problem with that is by the time they get down to one little part they're not sure about, they have focused their attention on this one little part and frequently forgotten about the big problem they're trying to solve. And so they've blocked off the idea of looking at other solutions. And so some of the examples we'll see today, we're going to try and reinforce the idea that if you go down this rat hole somewhere, down this rabbit hole, sometimes you want to pull back out of there and look around and say, maybe I want to go over there. Anyway, let's look at a question. Here's a Stack Overflow question. I have 3 of them for this talk. This is the links for them are on the bottom of the slides, or you can just search for the text on Stack Overflow and they'll pop right up. It says how to find the second maximum value of an array of strings where the size of a particular element can be 1024. You're not supposed to read slides, but I'm going to read a couple of these today because these are the actual questions that people asked. The array contains number, comma number, should this. I tried converting the array elements for any to integer and for any number less than 2 billion mumbledy. It all works, but I cannot convert it to integer if it contains number bigger than this. Is there any way to compare these numbers? Okay. That's the entire Stack Overflow question. Yes?
I'm a little confused already. It says an array of string, but they are string. No, sorry. I didn't see the quotes. Got it.
No problem. Leon did not see the quotes. He thought they were numbers. Okay. There, I repeated the question. Anyway, this is the entirety of the Stack Overflow question. Right there. It's a little incoherent. So, you ask, you start making comments on the question. What do you mean? What are you really trying to do here? Right? Clearly he wants to find the second maximum value, but okay. So we asked a bunch of questions, and we established the following facts. The data is a series of strings. Okay, fine. Each string can be up to 1024 digits long. He wants to find the second largest value in the data, sorted numerically. And his question was specifically, how can I convert these long strings into a number that I can then compare against the other entries? So let's just think about that for a minute. Okay? This is a lot more information. If we look back at the previous one, he has an example, a small example, but it's hard to get from there to here without several rounds of back and forth. I was talking to Lisa Lippincott last night about these kind of things in Stack Overflow, and she had a flippant response, which is still very, very true, and that is, if you want better answers, write better questions. Yeah, the better you write, this applies not just on Stack Overflow, but almost everywhere. When you're asking for help, the better question you write, the better answers you get. Anyway, so, all right, here we go. So we thought about this for a little while. He still wants to convert them to integers and compare them. So some other user on Stack Overflow, not me, provided the following comment. He says, you want to write a comparison function that compares the strings numerically, and he provided details. How you do it. It's basically string without a leading dash is always greater than one with a dash, right? Negative numbers always come before positive numbers. Strip out the dash and leading zeros, and then you just say longer numbers are always bigger than shorter numbers. But you have to actually, if there was a leading dash, you have to flip that. And if they're the same size, well, you can compare them lexicographically. You can just compare the digits. You don't have to actually convert them to numbers to do all this. And then he said, and step 2, call nth element with this custom predicate to find the second largest value. And I didn't, he didn't put in here step 3, profit, but that's where we're going to be. So is this an answer to the question the original poster answered? OP, original poster. No, it's not, because he wanted to know how to convert the strings to numeric values. But it does solve the problem he was trying to solve. Okay, he was trying to solve finding the second largest value when interpreted as a number. But you don't have to convert it to a number to do the comparison. Okay? And so by stepping back from the specific question that the person answered, we arrived at a solution of the problem. The problem he had without the part he was stuck on. And that's a really nice thing. Frequently, you can get that. You can solve a problem a different way. All right. Anyway, and then I chimed in because I like making trouble. And I said, fun question. Which of these is better? Nth element, begin plus 1, end, or partial sort, begin plus 2, end? So how many people here know what nth element does? About half. Okay, nth element is one of the sorting algorithms in the standard library. And in particular, you give it begin and end. The first and the third parameters denote a range, and the middle one is somewhere in the middle of the range. And it permutes the range. I'm using range to mean a sequence. You permutes the sequence so that everything to the left of the pivot element, the middle one, is less than the pivot element. Everything to the right of the pivot element is greater than, and the element that is at the pivot element, in this case v begin plus 1, is the element that would be there if the entire range was sorted. Okay, you can think of this as a pass of a quicksort algorithm if you'd like. Choose a pivot, make sure that's in the right place, and then partition the sequences into everything greater than, and everything less than. It doesn't say anything about the order of the elements to the left or to the right, just that they're all less than or greater than. Okay? So it's a partitioning operation, but it's also, an important building block for building sorting algorithms. Now, partial sort, on the other hand, partial sort takes a begin and a middle and an end. And what it does is it says, okay, I'm going to take the elements from begin to middle and put them in the right order as if the entire sequence was sorted. Okay? The things from middle to end are all going to be greater than the things from begin to middle. But they're not going to be in any particular order, but the ones from begin to middle are going to be sorted. So partial sort is like, I have this sequence, I need the top 10 elements. Well, you run partial sort. You don't sort the whole sequence, million element sequence, and then just take the top 10. You call partial sort, say, I just need the top 10, and we'll do that for you. And the reason you do this is because it's cheaper, right? It's less work to shuffle the top 10 elements to the start of a sequence than to move everything around and get everything perfect when you don't need that information. So there are a whole bunch of sorting algorithms in the standard library, okay? And they do slightly different things, and they have different complexities, and some of them are much cheaper than others. And so when you're doing a sorting operation, you want to think about which one of these is the best for you. You don't want to do extra work that you then throw away, right? In the examples we're talking about here, he wants the second largest thing. You have to identify the largest thing to find the second largest. But after that, you don't really know. I mean, you could just sort the entire 1,000 elements and then pick off the first two, but why do that when you don't care about the order of all the other ones? Anyway, so which is better? Okay? Nth element or partial sort with these parameters. Okay? For the problem that we're looking at, these do the same thing. They put the smallest element in V0 and the second smallest element in V1. Okay? This is a very peculiar circumstance where these two calls do the same thing. Now, I pulled a switch here. I went from talking to second largest to second smallest. And I did this for two reasons. The first reason is because partial sorts like to shuffle things to the front of the range that you're talking about. And second, because it makes the code smaller and it makes it easier to fit on slides. Okay? We can get the second largest with partial sort by inverting the comparator to return greater than rather than less than. So this doesn't change the approach we're taking, the meaning of the results we're getting. It doesn't change the problem we're attacking. It's just easier to talk about second smallest instead of second largest. Okay. Now, obviously, this is very specific to the fact that we're looking for the second smallest element. This wouldn't work for, say, the third smallest element or fourth smallest element. And the analysis I'm about to do is, again, specific to the second smallest element. Interestingly enough, when I was reviewing presentations for this conference, for things that we're picking up, somebody proposed a talk, and they gave as background a set of slides for another talk they had given at a different conference that mentioned this exact same problem. Now, the talk was in Russian, so I don't know how it was for C++ Russia, and it was in Russian, so I don't know how the talk actually came out. But I thought it was very odd that, exact same problem, using nth element versus partial sort for finding the second largest thing. Okay, anyway, onward. So So I said, which one's better? And somebody responded, well, nth element's going to be better because its complexity is linear. That's what the standard says. It's on average, linear on average. And that partial sort, the sort's complexity is approximately last minus first times log middle minus first comparisons. Okay, roughly linear, roughly n log n, you'd say, okay, nth element is better. But that's a remarkably imprecise set of specifications. Really, there are two operations that you want to think about when you're doing some kind of permutation algorithm. Okay, and sorting is just a permutation. You want to think about the number of comparisons. How often do you compare a pair of values to see how you order them? And the other thing is when you move things, right? The canonical move operation is swap. How many swaps happen? Okay, and depending on your data types, one of those could be noticeably cheaper than the other. One of them can be very expensive. If you're looking at strings, swapping strings is actually fairly inexpensive, assuming you're not having a custom allocator. Swapping ints is easy, right? Read, write, 4 instructions. Swapping, a megabyte of XML data may be cheap if it's just swapping pointers, or it may be really expensive if you actually have to copy that megabyte of data. You don't know. I don't know in general. You would know for your data type. Anyway, so yeah, a good rule of thumb is that comparisons are cheaper than swaps. It's not always true, but it's a good rule of thumb. So what did I do? Yeah.
Middle minus first is 2, so the log of that is close to 1. So in this particular case, the sort should be approximately 1 million.
So yes, the comment was, if middle minus first is 2, okay, log base 2 of 2 is basically 1. And so last minus first times that is, yes, going to be very close to 1. And so in this case, you might expect that partial sort would be pretty close to linear. That when you're sorting just a little bit. But anyway, so what did I do? I wrote me a class. And it says let's find out. So here's the class. The class is called logger. It holds an int, right? And then I wrote a bunch of comparisons like this. This is the less than. It takes 2 of them by const reference, and it returns the less than on the one field it holds, the int field. But the important thing is it has a side effect. It increments a global variable, says, hey, I did a comparison. And I did this for all the other operators. Less than or equal, so on. And then I did also for swap, I incremented the swaps. This is not rocket science. This is a great way to actually investigate performance of stuff. Because these are the basic building blocks of permutation algorithms, are comparisons and swaps. And what did I find? I filled up a vector with a bunch of random data. And what did I find? I found that partial sort was a lot cheaper than nth element for finding the second smallest value. A lot cheaper. I mean, it was both far fewer comparisons, maybe half as many comparisons, but way fewer swaps. If you believe swaps are expensive compared to comparisons, this is a big difference. Now, when I say lots cheaper, okay, all of these ran in, even for 1 million elements, these ran far less than a millisecond, okay? This was no discernible wall time. But still, 420,000 swaps? Yikes. And then I tried it with a bunch of different random values. I was using, Merced and Twister to generate random values. And I tried this with picking up various points in the sequence, and yeah, they're all about this. That's very consistent. This was using libc++. You might want to try it with other standard libraries, but it's pretty clear that on my machine, partial sort is a much better choice for this, even though it's not the algorithm you would think to reach for. Okay, but can we do better than this? And now we're going down the rabbit hole. Can we do better than this, right? If we chose not to use a general purpose algorithm, maybe write our own algorithm, really we need two swaps, right? We're assuming that we want the same behavior as nth element or partial sort here, because that keeps the comparisons easy. We really need two swaps. We figure out where the smallest one is, we figure out what the second one is, and we swap them into place. Right? We should be able to do two swaps. We kept two iterators going through, one holding the current smallest entry, one holding the second smallest. We wouldn't need to move anything until the very end, until we got to the end, and then we swapped two of them in place. We have maximum of two swaps. We might have one, we might have none. If the lowest one was already there and the second one was already there, we might not actually do any swaps. But yeah, this is at this point, just a sec. At this point, this is we're deep into micro-optimizing things. Question?
This is a question from online, and it's actually going back, I think, one slide.
Okay.
The question is, wouldn't, for the first question, comparisons be more expensive? Swap is just swapping pointers.
Yes. So the question is, okay, the question's going to be on the tape, yes. For the original data set, absolutely that where you have a bunch of strings, comparisons are going to be fairly expensive. Swaps, if it's just const char stars, then yes, swap would be swapping pointers. So here's an example of where the comparisons are more expensive than the swaps, because the comparisons have to walk the strings and do lexicographic, individual character compares. Yes, we have another question.
Question is, isn't this standard library implementation specific though? Did you compare different standard library implementations?
I did compare libstud.c++, but interestingly enough, libstud.c++'s version of partial sort didn't call my swap overload. And so I couldn't get a count of how many swaps they were. They just do move assignment instead of calling the swaps directly. So yes, it is implementation of the standard library implementation specific, which is why I said I did this with libc++. So yeah, for libstud.c++, it said no swaps. But to go back to the previous question, even if comparisons are more expensive than swaps, you look at this data and you say partial sort is still a win because it's far fewer comparisons, and it's almost half as many comparisons, or rather say nth element is twice as many comparisons, 1223, 1,000 something to 2,100, 10,000 to 23,000, 100,000 to 186,000. Did I do that right? No, 1 million to 1.8 million, 1.9 million almost. So in this case, even though comparisons are more expensive, it's still, nth element is a lot more comparisons. Yes?
Have you tried benchmarking the cache invalidation?
Have I tried, no. Benchmarking cache invalidations, I have not. Okay. Now, I know that modern computing, it's all about keeping your caches hot, but I'm looking at algorithmic complexity here. Okay? All right. So we're going down the rabbit hole now. All right. So this is half of this algorithm that I called first two. Okay? Half because this is what will fit on a slide. Okay, let's look at this. I take the first two elements and I do a comparison to see which of them is smaller, and now I have The smallest so far and the second smallest so far. And then I walk through the rest of the sequence, and if it's less than either of these, I say this is a new smallest or a new second smallest. I'm assuming random active access iterators here for no good reason. Forward iterators would be just fine. You could rewrite this code trivially to use forward iterators, but I didn't. There's code after this that wasn't fit on the slide, and that actually does the swaps. It's a little bit complicated because, what if the smallest element is in the second position and you swap, and then you have to take into account of that when you swap the second one in, things like that. Anyway, so what are we doing here? We're, like I said, every element after the first two, we're doing a comparison to see if it's less than the second smallest. If it's not, we're done. Okay, if it is less than the second smallest, we check, is it less than the smallest? And if it is, we say, okay, this is the new smallest, and the old smallest is now the second smallest. And if it isn't, we say, okay, this is now the second smallest. So how many comparisons will this do? I see you. How many comparisons will this do? That depends on how the actual data. Okay? If you give it pathological cases, like say increasing data, the first two will be the smallest and the second smallest, and this entire loop here will never replace either of those. And so you will end up with n comparisons. If you give it decreasing data, okay, every single time you go through this, it will be less than the previous smallest, and you will end up with 2n comparisons. Now, given already sorted data, you would expect to see between n and 2n comparisons, and actually, usually much, much closer to n. Because as you go on, you get something that's closer and closer to your smallest data, and each one then is probably greater than your second smallest, and you don't actually do the second comparison. Yes, question?
The question was actually retracted, but it was why swap? They were wondering why you were using that, since the original problem was to find an element, not do a partial sort.
Why I was doing doing swap to, because the original question was about finding something. Well, the original answer was calling nth element to find the thing. And so I was just taking that approach and running with it. Certainly we could write an algorithm that didn't do any swaps at all, just did searches. I mean, you could just take this, right? And at the end of this, the iterator second smallest would be referencing the second smallest element. I did the swaps basically so that I could compare it to the results of nth element and partial sort. So yes, this is a related problem to the original poster. Okay. And so then I ran this and get some data. And it was a little surprising to me that partial sort, I've dropped nth element off of this list because if I include nth element, these numbers won't fit on a slide. That the number of comparisons were identical. Which is interesting because I believe that my algorithm first two here is doing a minimum number of comparisons, at least for this approach. And it seems that partial sort is doing the same number of comparisons. Now, you look at this and you say, okay, yeah, partial sort is doing a few swaps, a ton of swaps, because you remember the old thing. We were comparing here, nth element was doing just tons of swaps, and partial sort was doing very few. And the algorithm I just wrote, first two, is only doing 2 swaps. Right? We know it will only do 0, 1, or 2 swaps because it knows, rather than being a general purpose algorithm, it's an algorithm that knows it only wants 2 results. Okay, so we've done better than partial sort here.
But not as much better as you would expect.
I was not as much better as I was expect. Yes, I had not thought so much about the number of comparisons in partial sort, and it turns out it's doing a really good job on the comparisons, of minimizing the comparisons. So yeah. So the next question is this actually worth doing? The answer is almost certainly not. Okay? It's not really worth doing. First, because the original poster's question on Stack Overflow really reminded me of a homework problem. Okay? Probably not. But if you're in a situation where this is the hot path of your program, right, and you need to find the second largest or second smallest something, and in a sequence, and the elements of sequence are expensive to swap. If you need to shuffle them at the beginning, if they're expensive to swap. I mean, if you don't need to shuffle them at the beginning, then yeah, you can just implement it. You can implement the first this much of this algorithm and just find the largest or the smallest and the second smallest. Okay? But if they're expensive to swap, this could be a win for you. I suspect that the circumstances where this would be a win for someone are really, really small. These are very, very specialized circumstances. On the other hand, you're probably much better off using nth element or partial sort. And nth element is like what I would reach for first. And I would try that and see if in fact it does what I want, the performance is acceptable. The fact that partial sort works here, does the same thing here, is an artifact, a happy coincidence, if you would, of the fact that we're looking for the second largest element. Okay? If we were looking for the 5th largest element, yeah, partial sort would not be the right tool. Anyway, but on the other hand, what do we learn? We learned something about algorithm complexity. We learned about writing algorithms to solve a particular problem. When you go to less general solution, you can get better performance. We learned about measuring our results. Anyway, this is, and whenever I do this, and I do this every now and then, just take a problem and just kind of, just keep diving down and keep trying different things, I always learn something. This time I learned that partial sort on a very small thing, when you're sorting a small portion of a sequence, can in fact do a really good job. Yes?
Target is just finding the second largest or second smallest.
Mm-hmm.
So, because I think that this is maybe quite a linear search, and just considering 2 elements.
Mm-hmm.
Right? So the number of the comparison is exactly the same as the size of the algorithm.
Mm-hmm.
So just I wanted to know that why we should just consider partial sort or nth element.
So if you remember, the nth element did far more comparisons as well. The question was why, if my algorithm did basically a minimal number of comparisons, and so did partial sort, why shouldn't we think about, instead of partial sort, why don't we think about comparing partial sort and nth element? Well, we didn't know that partial sort was doing a minimal number of comparisons until we did the work. I did the work of writing first 2. But the other thing, if you go back and look at the original benchmarks I did here, nth element did far more comparisons and did far more work, which was quite surprising to me. But it did 80% more, 80, 90, maybe double the number of comparisons. and a lot of swaps. So that's why I dropped nth element off of this very quickly, because for this case that we're looking at, nth element is far more expensive even than partial sort. And so then it was, can I do better than partial sort? And the answer is, yeah, but not very much better. Did that answer your question?
Yeah.
Okay, good. Okay. Yeah, I found it interesting that the number of comparisons are exactly the same. I tried, picking up several different places in the random number sequence, and the numbers change, but partial sort and first two always seem to do a minimal number of comparisons in this case. I'm impressed. Whoever wrote the partial sort algorithm, Howard, for libc++, not me, I'm not claiming credit for this, I am, did a really good job. Okay, anyway. Is this worth doing? Probably not. Okay, a different question. Wow, I'm gonna have to speed up. Okay, this is a different question. Basically, the poster is trying to use the erase remove idiom on a string and passing stud IsPunk to remove punctuation from a string, and is failing to compile. Here's his code, remove if, stud IsPunked, and he gets an error that says remove if, unresolved overloaded function type. His question is, now I guess strictly speaking, the stud IsPunk callable's parameter type is an int and therefore doesn't match the range's element type char. However, char is a numeric type and it should be convertible to int. So he's, why are my chars not getting convertible to int? That's his question. Okay, so if you read the error message, it says, has a key phrase there. It says, unresolved overletter function type. What does that mean? It means that there are multiple calls named IsPunk in namespace stud, and the compiler doesn't know which one he means. Okay, if you go searching through the headers or the standards or whatever, you find out that in C-type is IsPunk that takes an int. In locale, there's IsPunk that is a template in IsPunk that takes a char t, some character-like type, and a locale, because punctuation, it can be locale specific. Okay, he almost certainly means the first one, right? But the compiler says, you want to take the address of IsPunk. I've got two, which one? I have no idea which one you want. And so I'm just gonna throw up my hands and say, unresolved overloaded function type. Overloaded is the key word there. Overloaded means there's more than one. Okay. You could say, well, if I just don't include locale, there will only be one visible to the compiler. And then maybe it'll work. The problem with that is that other standard library headers can include other standard library headers, and you have no control over that. So really, that's not a good way to go about things. You won't find that locale will show up in your includes at odd times. And it certainly isn't portable because different standard library implementations may have different include patterns. Anyway, okay. So, but there's another problem here. And the problem is that the standard specifically says, up in the library introduction materials, that you don't get to take addresses of standard library functions. It's not allowed except in a very few exceptions, and those exceptions are listed. Those exceptions basically are all in IO streams. They're IO streams manipulator functions like endlen or, bool alpha or things like that. Those are actually functions. And you take the address and you pass it to a stream to do things. In particular, the standard is very clear in the library introduction material that just because it says, here's a function named IsPunk that takes a char, there may not be a function named IsPunk that takes a char in your standard library implementation. What it says is if you write IsPunked, open paren, and it doesn't take a char, it takes an int, sorry, and an integer value there, that call will do what the standard says it does. Okay, there might be, in your standard library, there might be IsPunk, int, comma, fooby equals default value, bar equals default value, baz equals default value. It may take, 5 parameters, but all but the first one are defaulted. So there's a restriction on taking the address of things because you don't know really what's there. Anyway, So fortunately, there's a really good solution to this if you have C++11. If you don't have C++11, you can do it, but the C++11 solution is there. Use a lambda. Okay, why do we want to use a lambda? Because we don't take the address of IsPunk, and we let the compiler disambiguate the overloaded function set. We're calling IsPunk with one parameter. That means when it builds the overload set, as if you went to Barbara and Ansel's talk about name resolution, they went on and on about building overload sets and resolving them. The second one, the one in locale, will not be valid, not be viable, because it takes 2 parameters. And so you won't get this ambiguity that you got where you just took the address of it. Okay? Takes the correct overload, solves both our problems. Again, this doesn't really answer the original poster's question, which was, why are my characters not getting promoted to int? That's the wrong question. Okay? Why are they not implicitly getting promoted to int? In this example, they are getting implicitly promoted to int because IsPunk takes an int. Everybody good on this? Again, we're trying to solve the original poster's problem, not answer his question. Because his question was misguided. I don't want to say wrong, but it doesn't get him any closer to answering your question. But there's one more problem here. Are there any restrictions on what you can pass to std IsPunk? It takes an int. And yes, there are. If you can go to dig them out of the C reference if you want, because that's, IsPunk is a C call and std IsPunk wraps this from your C library. But you dig it out of the C reference, but CppReference has done this legwork for us, which is great. If you're not familiar with CppReference, it is a great reference website, cppreference.com. There's a link down here for IsPunk. Tim Song and the rest of the crew there do a great job. It is, if I don't have to read something in the standard, it's all good. And so it's one of my first stops. You should bookmark it, and if you have any questions about the standard, that would be my first place to go. Anyway, but it says behavior is undefined if the value of ch, and in the example on CppReference, it doesn't use c like I've done here. It uses ch. Fine. If the value of ch is not representable as unsigned char and is not equal to EOF. Okay. So, what does this mean? That means if you have you're working on a platform that has signed characters, and most all of you are, and you have a character whose representation has a signed bit set, i.e. it's a non-ASCII character basically, and you pass it to IsPunk, you get UB. Right. And why is this? Because a lot of standard library, or a lot of C libraries, basically they have a 256 element table. And when we call IsPunk, they take that value and use it as an index into the table. And if your characters are in the range -128 to +127, well, you're going to step off the beginning of the table and not get the results you want. They don't usually have, the C libraries I've looked at, they have one table that has a bit mask, for punctuation and alpha and so on. And basically they step into that array, pull the entry out, mask off the bits they're interested in, and then return 1 or 0 to say IsPunk, is alpha, is digit, is all of that. But anyway, the point is that it has to be representable as an unsigned char, which basically means 0 to 255. Minus 40 is not in 0 to 255. So what can we do here? Well, we can take advantage of, yes, Michael.
Do you know what the history is behind IsPunk taking an int? Is it just so that we get interval conversions? Those are nicer than.
Okay, so the question was, do we know the history behind why IsPunk takes an int? Is it because we get interval conversions or what? No, I believe that all the character-based things in the original C library, which is where this came from, take an int because they want to have all the values of char plus EOF. EOF being -1. That's my belief. It may be more nuanced than that, but certainly that's it. Liam.
What did I mention? Why do we care about this issue? Because the original example used IsPunk with the same restrictions apply to the original code as to the lambda-based code.
Yes. Yeah, there's a problem here in the lambda-based code.
So why do we care?
Why do we care about invoking undefined behavior?
Yeah, so we're just dealing with characters in the string.
Yes.
And you're saying those characters might be negative,
They might be negative.
and we care?
We care because IsPunk will do bad things, something. It will probably just return garbage values, but its undefined behavior could do almost anything. Could segfault, could crash, could.
Can't we just make it a precondition that the characters are ASCII characters?
Well, that's the precondition to IsPunk.
But I mean, we can make the code that was the basis of this example have that precondition.
Yeah, we could. Or we can do this. Okay? We can, in our lambda, we can take the parameter as unsigned char, where it will be implicitly converted, basically the same bit pattern. And instead of being in the range -128 to 127, it will be in the range 0 to 255. And pass that to IsPunk. And then that will do the right thing. Just one sec. So what do we do here? We got three things, right? We don't take the address of standard library function. We let the compiler find the right overload for us. And we avoid the possible UB. Yes?
Is that really the right thing though? Because if it was a negative char, we just force it to be an unsigned char. We change the
value, but we haven't really changed the bit pattern. So your C library is going to have a table of 0 to 255 of all the characters, okay? Your choices are really, if you have -40, your choices is don't call IsPunk, or take that bit pattern, which turns out to be, what, 160 something? I don't know. And say, is that a punctuation character? Is that the answer you want? Really what you want is you're going to want this second overload. If you have a lot of characters like that, you're going to want the locale specific IsPunk, but you're still going to have to convert it to unsigned char. So this is better. This is demonstrably better, even though and the C library will, in fact, the C library is used to seeing things like this, seeing, things shifted into high ASCII that would be less than 0 on signed characters. So this is a very common pattern when dealing with characters that do not fit in 0 to 127. It's not always right, but it's right more often than not. And we avoid the undefined behavior, which is always a win. Any other questions? Any questions from online? No. All right, I have one more question, and sadly, we're at 10 till, so I'm going to really, really power through this. And unfortunately, this is a kind of a cool thing, so I'm going to talk really fast and put the slides through so everybody can see the slides. The question is, I have a tuple A, B, and C, which I can order using the obvious ordering, I compare the A's, I compare the B's, then I compare the C's. Okay? Have a map of them, but I want to do a search on just the first two things. Just the first two things. So I want to find all the entries in the map where the A's match and the B's match, and I don't care about the C values. Okay, and he wants to do this, in the title he says he wants to do it in O(n) time. Well, that's easy, right? But then here he wants to do a O log n time search. All right, so how do we do this? This is actually right in the standard library's wheelhouse. In C++14, we added the idea of transparent comparisons, the ordered associated containers. You can define a comparison function that takes parameters of different types and compares them. This was originally done, the motivating case was for sets of strings where you had a string literal that you wanted to say, is this in the set? And you didn't want to create a temporary string, use it for comparisons, and throw the temporary string away. So you want to just compare the const char star, the null terminated string, without actually copying it into an std string. So the way you do this is you write a comparison function that has multiple operator parens. Here's an example of one. Okay? It has one that takes two const strings, and then two others, one that takes a string and a const char star, and one that takes a const char star and a string. Okay, quick. How do you apply this to the original Stack Overflow question? You implement a comparator taking the full tuple, A, B's, and C's. Okay? You need that for the map, or the set. You need that because it imposes an order on the set. You implement a comparison function taking tuple A, AB, and tuple ABC, and one taking tuple ABC and tuple AB, and you make sure they all take things by const and are const on your comparator. And if you do this right, you should be able to call equal range on your set and get a set of values back. Here's a link to a GitHub gist that implements this. I'm not going to go through this code because we're 5 minutes away from being the end of the day. But this turns out to be very straightforward. It works really well. It leads to some interesting things, some results that you might be surprised of. You have a set, you have a value, right? You say, how many elements with this value are in this set? It's a set, it doesn't have duplicate values, right? There's only one. No, there can be more than one. In this case, where you're testing partial things. You know, if you have, say, 3 elements that have the A's and the B's matched, but the C's are different, they're fine in the set. But if you just search for A and B, you know, the tuple AB, you could get a count back of 3. So there are 3 of them. Equal range is your friend here. Equal range returns 2 iterators, the beginning of the things that match and the end of the things that match. Equal range, you would expect to have a single thing in it because, you know, count can be implemented as calling equal range and then saying how many elements are in that. But anyway, you can call equal range. Again, this is not quite the question that the answer that the original poster wanted. He wanted to call find and then iterate forward. But I'm saying equal range is better because equal range just hands you a pair of iterators that you can iterate over. You don't have to check for the end. You just say when you're at the end anymore. You don't have to do any more comparisons. Anyway, just some cautions about this technique. This is a very powerful technique, but its utility is really, really limited. Okay? Because the set orders the elements in the set, the map, whatever, orders the elements in the container according to the comparison functor that takes 2 elements, 2 things that are the key. So in this case, it would be tuple ABC. Your comparison function that takes an ABC and an AB has to implement the same sorting order as that. And so you can find things where the A's and the B's match, but you can't find things that where the A's and the C's match because they'll be in different places in the map. There won't be a range of them. And obviously, this doesn't work at all on the unordered containers because they're, well, unordered. I'm sorry I went so slow on the first parts because this to me is a really interesting thing. Anyway, feel free to go look at the code that's up there. That's, it's a GitHub gist. It's a little small program that implements this. You can download it and play with it and try your own things. All it does is it defines A, B, and C as very simple structs, defines some comparison functions, and then takes a set of them and puts like 5 things in it and calls equal range to do a partial search and says, oh, look, I got 3 of them back. Anyway, fun thing to play with if you like playing with those kind of things. Anyway, general comments, okay? When you're working on a problem, and we see some of this on Stack Overflow, when you're working on a problem, keep the big picture in mind. Keep coming back to what you're trying to solve. Remember the first problem? We went down that rabbit hole a long way, and we got to the bottom, and it's like, is this worth doing? Probably not. I can think of some really rare circumstances it's worth doing, but we learned something along the way, and we explored an alternative and said, no, that's okay. That's interesting, but it's not good enough. It's not, it doesn't do what we want well enough. That's fine. Don't be afraid to try another approach. If it doesn't work out, hey, it's okay. You've learned something about the problem. You've developed a new skill. You've learned stuff. And when you're stuck, try explaining it to somebody. Many, many years ago, I attended a talk at an Apple Developers Conference. Oh, geez. Lisa, do you remember when that was? 1994 or something like that? Anyway, and the gentleman who was giving the talk said, the best debugging tool you can have is smart friends. Okay? You have a problem, you go find a smart friend, and you explain it to him. And what's going to happen? You explain it to him, you walk through, I'm doing this, I'm trying this, I'm trying this, I'm trying this. And you get 2/3 of the way through, and you say, oh, of course, I know what I'm doing wrong. Thanks, and you walk away. That's the first thing that could happen. What's the second thing that could happen? You explain it to her, and you're sitting here, and you're explaining it to her, and you're going all the way through it, and you say, up, and you get to the end, and she says, Well, I'm not really sure, but this looks wrong to me. And you say, great, yes, that's it. Thank you very much. Okay? Or the third case is, you explain it to your friend, and you go through it all at the end, and at the end he says, beats the heck out of me. And then you feel better because he's smart, and he doesn't see it either. It's not just you being blind. You can be blind together, or maybe this is really hard. But in any case, you've been reassured that you're not missing something obvious, right? All 3 of those cases, you're better off than you were before. 2 of those 3 cases, you have a solution. Another thing that works really well for me when I'm stuck on a problem is I write down the problem I'm having. And for me, actually putting, well, if you'll excuse the expression, words on paper, writing things down, spelling them out, sometimes gets me to the point of, oh, yeah, that's what's wrong. I have tried writing Stack Overflow questions, even, as a way of clarifying my thinking. I have so many assumptions in my head when I'm just puzzling around a problem. It's like when I write it down, it forces me to actually put those assumptions out there in print in front of me. And I'm like, oh yeah, no, that's not true. Oh, okay, if that's not true, then it's like, great. So Explaining things, even if it's just explaining it to yourself, is a really, really powerful tool for solving problems. And that's kind of the takeaway here, is that when you get stuck, try different things, whether it be, take a step back and try to solve a related problem, or try a different approach, or try to explain it to somebody. Improve your understanding of the problem is really what I'm saying. Okay, none online. I got one more slide. Thank you for coming.